Hello everyone. In this video, I'm going to talk about computer system modeling using stochastic approach. The computer system can be modeled in two different approaches. One is stochastic modeling and another is cycloaccurate modeling. Everyone knows the cycloaccurate design is more precise in the evaluation, but choosing this approach for all the cases is not efficient. We have to use cycloaccurate modeling to verify the functional correctness of the system, but for other aspects like power analysis and performance evaluation, it will cost more design time and testing time. Designers can choose this cycloaccurate model for these purposes, but it is better to choose the stochastic modeling for faster simulation with lesser overhead. In comparison, each has its own advantages and purposes. The designer has to choose the approach that benefits them the most. The cycloaccurate model is used to implement the detailed behavior of each instruction and operation, while in the stochastic case, it implements the model at the system level with less complexity and overhead. The main purpose of the cycloaccurate model is to evaluate the correctness of the system, but with the stochastic model, the designer does not have to worry about the correctness. Instead, they can focus on the performance of the system by selecting different parameters with different use cases. With cycloaccurate model, scaling the system is not an easy task. It can increase the complexity of the system. But with the stochastic model, the user can expand the system easily with less overhead. Cycloaccurate design can be helpful in debugging the model to optimize the system in terms of timing. But with the stochastic model, it can be helpful in analyzing the system performance through different configuration and also in observing the use cases that fail in those configurations. Stochastic modeling can also be beneficial for power analysis due to the less complex implementation. Stress testing the cycloaccurate model is not an easy task. It will consume a lot of time, and sometimes it will be hard to debug in certain situations. But with the stochastic case, it provides easy modeling of the traffic profile to create a wide range of traffic and stress test the model with different configuration at a faster rate. Analysis can be done using the stochastic modeling. For a computer system design, the designer wishes to analyze the performance of the system by checking the CPI, MIPS, total number of instruction executed, and the total time taken to execute the given workload. Even though these can be observed using the cycloaccurate model, the designer has to wait for a longer time as it has to execute each instruction and operation in detail. Also, recursive analysis using the cycloaccurate model will take a longer time. But with the stochastic model, the designer can observe these important statistics at faster rate, and also they can observe the activity of each stage or device as the complexity of the design is very less. They can also observe the power consumption of each device or the entire system to identify the areas where improvements are needed. Example scenarios that benefit from stochastic modeling. Assuming the correctness of the system is validated, but with the optimal configuration is not figured out. In this case, the designer can opt for stochastic modeling to design the system level model and stress test the model by sending the traffic with randomness and uncertain traffic profiles. Similarly, designer can use the system level model to configure the power for the entire system and also the cases where different operations consume different power levels. This will help the designer to select the optimal configuration and better power management policies. Let me open a demo model to explain the stochastic modeling. This is an architecture view of a 5-stage pipelined scalar processor. The internal architecture is constructed using the system resource block, which are accumulated here. And each stages or each functional logic is connected to the system resource using the mapper. Similarly, the pipelined stages are the pipelined stage operations are emulated using the delay block. This kind of modeling requires complete details of the possible flows, which can be reflected using the cycloaccurate design. The system resource block delays each operation for a specific time as per the specification. This approach doesn't care about the internal logic, but it achieves faster design and evaluation. In this model, the traffic is configured to send each task at a 30 microsecond delay, and each task contains 4,000 instructions. For the entire traffic, the 90% of them are ALU instruction, and 10% of them are load store instruction. Let me run the model and explain the statistics from this. Now the simulation is completed. We can observe the statistics and the plots that are designed in the system. At the end of each task, the design will provide the CPI, MIPS, and the total cycles taken to execute the system. Similarly, we can observe the time delay within the each pipeline stages. We can observe the average and number of packets processed by each stages. The designer designed an utility activity diagram where the user can observe the utilization of each device throughout the simulation. Along with this, the designer can observe the power consumption of the entire system as the instantaneous power and average power. So this is an example of a 5-stage super scalar processor in a stochastic modeling. Thank you.